Okay, I hope that's working now, everybody. Can anybody confirm? It's possible they've changed the URL on me. So I'll just repost. Okay, so the URL is different. Okay, great. Um, let's see if we can make this work, okay? So I'll keep the chat function open here. Chat is live. I can see Sean is here at least. So let's see if anyone else comes in. Only you, Sean. Okay, anyone else? Hello? I've got 4 viewers. Okay, great. Okay, let's go live. We'll just go ahead with this. Um, so right. So as you've done you've all done your, at least started your lab in TCP now. I'm going to do a couple of questions in TCP today from previous exams, which I hope will help better understand the question. So the subject of TCP. Okay, let me open an exam question. Okay, just trying to open an exam question here, guys. Okay, can you hear me now? So thanks to Carl for pointing out he couldn't hear anything. Okay, are we live? This thing drives me mad every week, so I thought I had all the problems sorted. Clearly I did not. Okay, so there's a bit of an irony here as well, that it's usually the network that goes down in the middle of a computer networks lecture. Okay, let's try and pick a question on TCP, and we'll see how we get on. So I'm just going to pick one of these questions here. Let's try, I can't remember which one was TCP, but we'll just go through it here. Okay, so question 3 is usually this kind of finite state machine diagram one. Okay, so this is kind of like TCP, or at least it's the start of TCP here. Actually, I've opened up the wrong one. Let me just. I'll go straight for a TCP one, and then we might go for go back N a little bit later. Okay, what's question 4? Okay, we've got a TCP one here. I'll try and make this a bit bigger. Okay, so this was from a few years ago. Part A is, what is the purpose of the receiver advertised window or wind in TCP? Well, so let's just go through that answer. So A. So what is the purpose of OR wind? Well, so TCP offers a service to the receiving side known as flow control. So and that's where OR wind comes in. So let's start off with that. So question 4A was, what is OR wind? And the answer, so this is TCP. TCP question 4, 2018. I think it's autumn. So what is OR wind? So answer. So TCP offers a service called flow control to the receiver. So what does that mean? Well, that means that if this is my sender over here, so over here is my sender. It's my application layer. It's my application layer here. This is my transport layer, and so on. And over here is my receiver. So this is the sender. This is the receiver. And same over here, application layer, transport layer. Remember our discussion about sockets. So I hope this is not too small, is it? Might be a little bit too small. Let me check the messages that are coming in from you guys. Too small? Or is it okay? Alright, well, I'm not getting any feedback yet. There's a bit of a delay. Anybody hear me out there? Still working? Content in the table is small. It's okay. Okay, thanks guys. So I'll make it a little bit bigger from here on. But anyway, it doesn't matter. This is the application layer. This is the transport layer. Application layer, transport layer, same thing, right? So in here is a socket. In here is our socket. and over here is our socket. And really, it's the two sockets that are connecting. So the application layer passes the data into the socket, comes out over here, gets packaged into a segment, TCP connection over to this socket. So it's as if these two guys are connected together, if you like. These sockets are connected. So when we have a TCP connection, we're connecting the two sockets together. Now, remember, we can't deliver anything out of order up to the application layer here. So when the packets arrive, we have to wait for everything to arrive in order, and only then can we deliver it up. And actually, the application will generally dip down. When things have arrived, will dip down and pull the data up. So there's memory available here. So there's a buffer inside. So socket has buffer. And it's only when, at certain intervals, the application will dip in, pull the data up from the buffer, from the socket, the buffer in the socket. Now, if we send data too fast in here, faster than the application, faster than the buffer can push it up, or rather the application can pull it up, then we're going to run out of space in the buffer. So socket has buffer, finite space. So what I'm saying is or wind. So when the messages come back, when the ACKs come back, when an ACK is coming back here, there's a field, the or wind field tells the sender how much free space is left in the buffer. So the idea then is that the sender will never send too many packets in here that are bigger than the available space over here in the buffer, and so we'll never overwhelm the receiver's socket buffer. That's the answer. Okay. Next part of the question. Sorry, where were we? Here we go. So identify 6 fields in the TCP header and give a description of each one of their uses. All right. So question 4B. Where did I put my green? There we go. How many fields did I ask you for? 6. 6 TCP header fields. Okay. Okay, well, if you're being smart, you'll say or wind. CA. So you've got one done already. What about your source and destination port numbers? So source, destination, port number. We know what they're for, right? They're used for, so what are they for? They're for uniquely identifying the sockets. And remember, the sockets with TCP are uniquely identified by a 4-tuple. The 2 IP addresses involved, source and destination, and the 2 port numbers involved, source and destination. So I'll just put that down here, 4-tuple. So now you've got 2. So this was 1. This was 1. This is 2. So 1, 2, 3 here. So you've got 3 so far. What about number 4? Let me see. What else have we got? we've got our sequence number. Our sequence number. So what is our sequence number? So I'll just rub that out. Our sequence number is the byte stream. So this is the byte stream number. And of course we've got our acknowledgement number. Which we know, so that's our fifth one. And we know that that is, you already know what this is. It's the next byte expected byte number expected at the receiver. Number 6. Number 6. So you've got a bunch of bits as well, you know, for establishing your connection, your SYN bit, your FIN bit. So I'll just put down SYN bit, FIN bit as two options. SYN bit, FIN bit. So use set high or low depending on whether you're establishing or tearing down a connection. Or tearing down a connection. So there's a bunch of fields. There's loads of other fields as well, and you can talk about them all if you want. But I only need 6, so I'll just do those 6 and move on to see if there's any questions coming in here. Can't see you still on the paper. Ah, nuts. I thought I'd done that. Oh yeah, still on the paper. Okay, well I'll go back to scene 3 here. Okay, so let's go through that. So I said or wind, you know, we've already covered that and the definitions over there. 2 and 3 would be our source and destination port numbers. Therefore uniquely identifying the socket. And remember there's a 4 tuple for that. Number 4 was our sequence number. That's the byte stream number we use to uniquely identify where we are in the stream. And the first one is always random, by the way, just to make hacking a little bit more difficult. Number 5, the acknowledgement number, kind of like the sequence number, except it's the next byte number expected from the receiver. 6, SYN bit, FIN bit, used to tear down and establish connections. Okay, next one, part C. Consider the 2 TCP connections that must share a link's bandwidth. One of the TCP connections has been running for quite some time and has built up a large TCP sending window. The second then starts with an initially small window. Long term, what will the relative throughput be between these two TCP sessions? Okay, so this is going to need me to draw. I'm going to be required to draw a graph. So just look at this for a second, and I'm going to rub out what I have here on the board. Just take me a minute, and then I'll go through how this works. So have a think about that. Hopefully you're figuring this out as part of your lab, actually. Okay, so I'll switch over back to the light board. Let's make sure you guys can still see me. Okay, if anything goes wrong, just shout. Okay, so the question was, so we're still on question 4, 2018 autumn. The question was, part C, 2 TCP connections. One already established using full bandwidth with large link usage. The second one just starting, little usage. Okay, so how do they end up using the same amount of the available bandwidth? That's the question. Let's go through this. So the best way to describe this, the best way to describe this is to use this graph that I have in the notes, where we'll show the bandwidth of the two different links. So TCP connection 1, so bandwidth TCP connection 1 and TCP and bandwidth TCP connection 2. Okay, so there's 2 connections. These are their bandwidths. Now, before I actually even go and show you the results for that, let's talk about how TCP deals with congestion. So we need to understand how that works first. So with congestion, so TCP window size, which of course is proportional to the window size the TCP is using is proportional to the amount of bandwidth it's using as well, or the capacity, the amount of the link it's using. Okay, so window size is always proportional to bandwidth. It's important to say. So this is over time here. So what happens essentially is once we get past the slow start, which we're not talking about right now, so we're moving past slow start, and we're saying, so the link will it'll have a particular value, say at time 0 here. So it'll linearly increase the window size. So it'll keep increasing the number of packets it's allowing into the channel unacknowledged in real time. So it'll just keep increasing the number of packets it's allowing into the channel, into the pipe at any given time, unacknowledged. So that'll keep increasing until inevitably it'll push it too far and it'll lose a packet. So once a packet is lost, we come down to half of the value we were at, half of the window size. So this is our C window. This is C window over 2. And then we linearly increase again until eventually a loss happens again. So loss, the event is a loss. So we've lost packet. And the same will happen again. This time it'll go back to this 50% of this value, and so on. And so on. So that's how TCP works. Can anyone confirm you're still hearing me out there? I'm just not 100% sure anymore. I'll keep going, but I'd really appreciate just anybody just let me know if everything's going okay. Okay, so where was I? Right, so once we understand that this is how TCP behaves, so it always tries to push more out of the link until it experiences a loss, and so on. So if there's two, imagine now we have two TCP connections competing for bandwidth on the same link. So what's going to happen here? So we'll imagine we're told here that in the first instance, the first TCP connection has a large link usage, so it's using up, we'll say, or all of the link. So we'll say the rate is or for the link. So we can imagine a time zero here, we're at this point here, or, right? So this is the link capacity. So at time, we're at this point here. So TCP connection 1 has a value of or, and TCP connection 2 has a value of 0. So this point represents the situation for the two different connections. Now, as soon as TCP connection 2 joins, it'll start to use up a bit of the bandwidth. This guy is going to suffer a little bit of loss. So we're going to end up with a situation where this guy is going to suffer a loss, so it's going to half its window size, and this guy's going to start eating up a little bit of the bandwidth here. It's going to start getting a little bit of the bandwidth here. So we'll put a point down here. So we've gone from this situation to this situation here. So it's R over 2 for this guy, and it's some small value here. So we'll start here. Now they both start to increase linearly. They both start to increase linearly at this point. So they're both trying to increase in time linearly. So they're both increasing, and then at some point they're going to get another loss. So bang, loss here. So we'll just say loss happens here, and we go over there. So now we've experienced a loss event, a lost packet. Both of them experience some sort of lost packet. So what happens now? Well, this guy's going to go to half the value it's at, which is here, and this guy's going to go to half the value it's at, which is, so if I go across here down, so this is the point we're going to go to. Okay, so this is going to go down to here. So this value is halved, and this value is halved as well. So they'll both increase linearly again until eventually a loss happens again. So they'll both suddenly go half the value again. So if I go between here and here, it's going to be along this line, somewhere along this line, and this one is also going to be half, so it'll be along this line, so it'll be around here. So bang to here, and so on until what you'll eventually find is they both increase again here, and then, sorry, that one wasn't very good. So they'll both do it again. So this time they'll come back to here, and so on. So eventually they'll just converge to this situation here, where they're just oscillating around here. So and that value there that they're oscillating around is R over 2. So they're just going to be both oscillating around a value of R over 2 here. This is the value for R over 2, halfway in between. They'll eventually converge on R over 2 here, both of them sharing the link equally at R over 2, at a value of R over 2. Okay, they're oscillating a little bit too high, a little bit too low, but they're converging around that value there, R over 2. And so that's how TCP provides for fairness when there's multiple TCP connections. So we go from this principle here to this graph over here. Okay, thanks Carl. Looks like everything's going really well. Thanks Connor. Back to the exam questions over here. Okay, consider a TCP and a UDP session that must share a link's bandwidth. Both of them would like to use as much bandwidth as possible. Long term, what will the relative throughput achieved by these two TCP sessions? Yeah, so simply put, so I'll just do it down here on the bottom. So this is D. So TCP versus UDP. So UDP will send as fast as it wants. And unfortunately for TCP will have this situation where UDP will be using up as much as possible. TCP will try to send something and it'll experience a loss very quickly. So it'll end up going down very quickly like this on this graph up here. So it'll half down again, and then it'll try and increase, but it'll immediately half again, try and increase, a loss will happen again, and it'll eventually come down very quickly to a window size of just 1. And then it'll just intermittently try to send something, and of course there won't be much bandwidth there because UDP is eating it all up, and so it'll just keep experiencing losses, and it'll go down to this situation here. So TCP will experience a series of lost packets in quick succession. C window will quickly go down to 1, and so UDP will just eat up the entire link capacity. Eats up full capacity. So that's why people say UDP is a selfish protocol. It's and TCP is much more what's the word I'm looking for? I suppose selfless or utilitarian or something. So it's providing a service to the entire internet by behaving like this. When this loss happens, it's because it might not be caused by the immediate link that's being shared with, say, other hosts beside it. It might be caused by a router somewhere on the internet and that's being overloaded. And so by reducing down the traffic it's pushing into that router, it's providing a service to everybody. UDP just keeps pushing. It'll never stop. So that's why UDP is not... If everybody used UDP for every application, nothing would work. The internet would grind to a halt. So TCP is essential. I forgot to put up the blooming window again. Sorry guys. I'll put it up again. I'll just quickly run through that. So UDP will send as fast as it wants. TCP will experience a sequence of links, loss events. So it'll try to increase. It'll keep hitting a loss, and it'll keep halving its window size until eventually it just drops down to 1 here. And so UDP just eats it all up. UDP will just take full bandwidth. Okay, suppose we want to modify TCP so that it counts the number of segments. Let me see. Yeah. Okay, so this is almost impossible. So let me just rub out my board here so I can go through this with you guys as well. So I leave this up on the paper for a minute. So have a think about why this is not going to work. takes ages to rub out. Where was I? Okay, so the question is, suppose we want to modify TCP so that it counts the number of segments that are lost in transit. Okay, so I mean the main problem here, I'll just put up the board again. Try not to make that mistake twice, 3 times. Okay, so the key, so suppose we want to modify TCP so it counts the number of segments that are lost in transit. So how many, how many segments are going to be lost? Well, the real difficulty here, of course, is that that you don't get individual acknowledgements coming back for every single packet. And so there's a cumulative acknowledgement going on here, right? So this is question E. Can TCP count lost packets? The answer is no. Remember remember that acknowledgements are cumulative at TCP. So ACKs are cumulative. So we don't get individual acknowledgements. So let's imagine the situation where we have a premature timeout. Okay, so if we have a premature timeout, we end up resending the packets, right? So imagine step 1 here, premature timeout. Step 2, resend packet. Step 3, received. Duplicate is received. Duplicate is received at receiver. So what does the receiver do? The receiver does nothing. So what does this mean? Well, this means that we have assumed something was lost. So the sender assumed something was lost. Yeah, but the packet was not lost. And because the receiver has sent a cumulative acknowledgement, it's going to send another cumulative acknowledgement. It's not going to send an acknowledgement for something that's already been acknowledged before the current window base. So it won't send. The receiver does nothing. It does not send a second acknowledgement. So we can never tell whether it was lost or delayed. So it's impossible to tell. So possible to tell if packet was lost or delayed. Okay, so is there anything else to say about that? Yeah, okay. Okay, so there's a few difficulties there with retransmissions and acknowledgements. So let's try and find another question here on, I'll go back to my exams here and we'll see if we can pick another one out. If you have any questions, just shout as well, please. Let's see. Okay, I'm going to put this one up here as well. So this is TCP, but also GBN SR. So this is from autumn 2019. So I'll just rub this out. I'll rub out the board here while you guys are reading that. Okay, compare GBN, SR, and TCP, no delayed acknowledgement. Okay, assume that the timeout values for all three, this is the bit I'm reading here, are sufficiently long such that 5 consecutive data segments and their corresponding ACKs can be received by the host B and the host A respectively. Okay. Suppose host A and 5 data segments to host B. A sends 5 segments to B. Second segment is lost. We have to get all segments over to B. Okay, so 15 marks here. How many segments has host A sent in total, and how many ACKs has host B sent in total? Answer the question for all 3 protocols. What are their sequence numbers? Okay. Guys, is everything? I see Oshin saying it's still on the paper. I thought I'd moved it back. Let's see. Let's see if I can press live here. Yeah, no, I'm definitely back. Okay. So let's do that. So we've got TCP. So this question, autumn 2019. 2019. Question 4, autumn 2019. So we've got 3 protocols to compare here. We've got A to B sending 5 segments. Second one is being lost, and we have to compare what happens for these 3 different protocols. So let's do the 3 different protocols here. So I'll have GBN here. Say we'll have SR here, and we'll put TCP over here. And this is our timeline. So we'll go all the way down here like this for GBN. Same for SR, A and B. And the same for TCP. A and B are sending these. So A is going to send 5 packets back to back. How many segments? What are their sequence numbers? Answer this for all 3 protocols. Can you guys still see me? I think everything's going okay, but it'd be great if you could just every now and then just say something. Okay, so did I say anything else? Five, second one lost. They have to all get over here. Okay. Okay, so did I say about the window size? I must have said the window size, eh? Sequencers, assume, so compute. So do I say what the window size is? I should have said what the window size is. Compare GBN, SR, and TCP. Assume the timeout values is sufficiently long, such that 5 segments and their corresponding ACKs can be received. Suppose A sends 5 segments, and the second segment is lost. In the end, all 5. Okay, I'm going to assume the window size here is 5 for everything, okay? I should have put that in there in the question. So I'm going to assume the window size is 5. Okay, so let's imagine our window size is 5. So we've got packets 0, 1, 2, 3, 4 here in the window. So we'll send them back to back. So we'll go straight over here. So all 5 packets are going to be sent back to back here for both protocols. So the first one is sent here, packet 0. And it's received over here, so we'll write down receive packet 0. Packet 0 arrives. Deliver it up. I'm just going to use an arrow for deliver it up to the application layer. Send ACK 0. Okay, so our ACK will come back here, like so. Meanwhile, our second packet, we're told, is lost. Our third packet, of course, has been sent back to back. What happens when our packet 0, so this is packet 1, packet 2. So packet 2 arrives here, discard. So we just discard packet 2. And we send ACK 0 again. A second time. And the same will happen with this one, packet 3 and packet 4. 4, same story. So discard. So I just send ACK 0. So what happens over here, so the first time we got back the successful ACK 0 over here, our window is allowed to move across. So now 0, 1, 2, well, imagine there's more guys here. 0, 1, 2, 3, 4, 5. So we'll imagine now our window has moved across. We're allowed to send packet 5 now. So at this point we're allowed to send another one, but it's going to be discarded as well. Okay, so what was the question again? How many ACKs has B sent in total? What are their sequence numbers? Okay. Yeah, so eventually the timeout is going to happen. You were told the timeout is just enough for I think it was 5 segments round trip time, right? So this would be the round trip time for, did I say 5 segments round trip time? 5 consecutive segments and their corresponding acts can be received. So five segments and their corresponding acts can be received. So this would be the round trip time just here. Okay, so this is our round trip time, or this is our timeout time down here. So timeout. So we're going to notice at this point that we still don't have ACK0 arriving here. We started our timer here. Timer starts here, and now we've got a timeout. So when the timeout happens with GBN, we resend everything that's in the packet. So all of these packets are 1, 2, 3, 4, and 5 is now being sent again. And we'll assume that they're correctly received this time. So this is 1, 2, 3, 4, 5, and the ACKs will come back here. This time it'll be ACK. So this time we'll just deliver it up. Deliver it up, deliver it up, deliver it up, deliver it up, and it'll be ACK 1, 2, 3, 4, 5. Okay, so with each one it moves the window across more. Okay, if you have any questions, just shout out. Let's have a look at how that plays out with SR. I might have run out of a bit of room here with this, but I might have to rub this out a little bit, but hopefully you get the idea for this one anyway. Okay, SR, same story. So I'll use orange here just to be a bit different. So we start off with our 5 packets going back to back. And I'm going to rub this out here because I have no room left. Okay, so we've got our window this time is a bit different. So our window will be, well, it's the same actually, sorry. 0, 1, 2, 3, 4. So I send 0, 1, 2, 3, 4 packets. This one is lost. This one is lost. So I've lost this guy here. Once again, that's what you're told. Packet 2 is lost, or second packet is lost. This time, so packet 0 is delivered up. Packet 0 is delivered up, and we send ACK0. So we're sending individual acknowledgements this time with we're sending individual acknowledgements this time for each packet. So this time it's ACK0. This time nothing happens. This time packet 1 or packet 2 is buffered. So because we've missed packet 1 here, we can't deliver it up. We're not allowed to deliver anything up to the application that's out of order. So we have to store it, but we'll still send ACK2 here. And of course each one of these has a timer as well. So now we've got pack 3, same story, buffer, ACK3 going to be sent back, and this is packet 4, buffer, and send back ACK4. So these ACKs will come back here, and as soon as this comes back, as soon as the first one comes back, we're allowed to move the window across. So the window, so now, the window will now be 0, 1, 2, 3, 4, 5, 6. So now the window is going to be these guys. So we've moved past the 0, and we're allowed to send packet 5. So it's the same story as what happened over here. The window moved across, and we were allowed to send the next packet. So we can send that one straight away. And of course that's going to be buffered as well. Packet 5 is buffered. And then ACK5 comes back. Now timeout is going to occur right here. So timeout will occur here. So our timeout, you're told, was the time to send 5 segments over and back. So there was an individual timer started for this packet here. So this timer starts here. So we can just go to here for our timeout. So what do? We resend only the one that triggered the timeout. So I just resend packet 2. This time it's received, or packet 1 rather. This time it's received correctly, and we deliver it up. And we deliver up all of the packets. Deliver up packet 1, 2, 3, 4, and 5. Sorry. Yeah, 1, 2, 3, 4, and 5. Everything gets delivered up. And we send back Act 2. So the window will just suddenly jump across here all the way to 6. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So suddenly the window has jumped all the way over to here as a result of that single acknowledgement coming back here. Sorry, drop my pen. Alright, now let's look at TCP. So TCP is kind of similar. It uses bits of both of these. So same story more or less. For this one I'll use a different color again. Same story. It's actually so the yeah. So what was I looking for here? I think I was looking for the triple duplicate, which would have occurred here. Yeah, sorry, the timeout. Where I put the timeout here was incorrect. So the timeout should have occurred down here. I told you it was the time. I told you the timeout would occur in the time it takes for 5 packets to be sent and all of their acknowledgements to come back. So that would be down. That would be down here. It'd be actually down here. So your timeout would occur down here. So your timeout would have happened here, sometime after here, and it would have resulted in that same story. Okay, so now let's go over here and see that with TCP it'll happen a little bit quicker. The only difference with TCP and SR is going to be after we get a triple duplicate here, so it's going to use cumulative acknowledgements, just like this guy kept sending ACK0, back every time. TCP is going to keep sending ACK0 down as well, but once it hits the triple duplicate, it's gonna realize that packet 2 has been lost, packet 1 has been lost, and it'll resend it. So it uses aspects of both of these. Okay, so same story. You've got your 5 packets coming over like this. Second one is lost. So the ACKs that come back, so this was 0, 1, 2, 3, 4. The ACKs that come back were 0. This never ACKed. Sorry, this never existed. But then the ACK that came back was 0, 0, 0 again and again and again. So the key difference between this one was we don't discard over here, we buffer. Buffer packet 1. Buffer everything. So we just buffer and buffer each time. When we get back this triple duplicate here, this is a triple duplicate. Which means resend packet 1. We realize the next one should be resent fast. So that gets sent straight away. So packet 1 is resent. It's received over here. And what we realize, it fills the gap. And so we deliver everything up. Deliver everything up. And this time the ACK that comes back is ACK. It's going to be ACK for the next packet here, which was 5. Now with TCP it's a little bit different. The acknowledgement numbers are always a little bit different. So the ACKs that come back are actually the next byte stream we expect. Now I've just left it the same here with the integer numbers just for simplicity and comparison. But actually what happens is it's the byte stream. So the sequence number here would be the byte stream in the data that we're actually sending. And then the acknowledgement number that comes back is the next byte we expect. In other words, whatever was delivered plus 1 in terms of the memory bytes. And that covers that part of the question. So what are the sequence numbers? Show simple diagrams. How many ACKs has sent B sent in total? Well, for both of these guys here, for SR and TCP, it's sent 1, 2, 3, 4, 5, 5 ACKs in total. It depends on whether we're including this guy here at the end as well. I didn't strictly say to do more than 5 segments, but you can see the numbers that are being sent back. There's way more acknowledgements coming back on this GBN. It's the same for both TCP and SR. Yeah, I wasn't clear enough in that example. I actually remember loads of students having that question. What's the window size? I should have been clearer in the exam question. What's the next part here? B, if the timeout values are longer than 5 times the round trip time and there are more than 4 segments, which protocol successfully delivers all 9 data segments in the shortest time? You can assume the second segment is the only one that gets lost and no ACKs are lost. So I'll just put that up on the board. Sorry. So this is the question. What if there's another 4 segments to be sent? Which one is going to be the fastest? So the answer, of course, is TCP, because the triple duplicate will occur before the timeout. You're told that your timeout is longer than 5 round trip times, so that's going to be way longer, way longer than your triple duplicate. So your triple duplicate will happen in just over 1 round trip time. Let's go back to the board and I'll just show you that. Okay, so for TCP here, you know, these guys are happening back to back. So the transmission delays between these is pretty small. So it's all propagation delay, really. So your 5 times the round trip time would bring you way down here somewhere. So the triple duplicate will tell you the loss has happened way before that. So TCP will send that quickly and it'll recover more quickly, and therefore it'll get to the end much more quickly than either of these these other 2 cases. That's all you need to say for that answer. So the triple duplicate will happen before 5 timeouts. Not the clearest question I've ever written. Not too impressed with it as I read it now. But yeah, sometimes you see it after you've done it. All right, I'm going to take a little break for 5 minutes because I tried to skip lunch setting this thing placed up, and I just need to eat anything. So I'll be back in a few minutes. I'll leave you with maybe one more question to think about. So I'll just dig up another TCP connection if I can find one. Let's see. All right, this is, let me put it up on the board. This is last year's summer exam, TCP and GBN. So host A and host B are communicating over it. You know what? I'll let you guys read it and I'll come back to you in a few minutes. Okay, hello everybody, I am back. Okay, yeah, I feel human again. Thanks, Reddick. Okay, so let's see, TCP and GBN. So host A and B are communicating over a TCP connection. B is already received from A all bytes up to byte 126. Okay. Host A sends two segments to B back to back. The first and second contain 80 and 40 bytes. And the first sequence number is 127. Port number is 302. Destination port number is 80. And okay, B sends an ACK whenever it receives a segment. Okay, fine. A. In the second segment from A to B, what are the sequence numbers? Source port number. Okay, that's reasonably straightforward. You won't get too much easier than that. So I'll just rub out the board here while you try and do A and B, I guess. I'm nearly out of this this Perspex cleaner. My kids keep using this board, so my markers are nearly gone too. Can I ask actually if you can see, can any of you see the previous recordings on YouTube that I've done? The previous streams I've done on YouTube, can you see those? So if anyone could let me know. As I've been editing them on YouTube, but I'm not sure if they're actually visible or not. If I need to press some post or publish or something button. Okay, getting some answers in there. Yeah, okay. I probably need to tidy them up. How many can you see there, Stephen Raddick? How many videos can you see up on YouTube? Is it just 2, or is it loads? In which case, I really need to clean them all up. Okay, look, I'll go ahead with this question here anyway. So back to the light board. All the previous streams. Wow. Okay, I better tidy all that up. Right. Something to do. All right, back to the light board. We're going to try and answer this now. So question was A and B are, so this, just to remind you, is January, so last year's summer exam. So question for summer 2020. A and B are communicating over TCP connection A to B, right? So again, we'll just put A and B along these two lines. So we're told that we've got two segments. So let's say this is segment 1 coming here. And you're told the sequence number here is 127. And there's a bit of a hint there. You're told that, sorry, 127, that previously 126 bytes have been delivered before these two segments. So that's the way it is in TCP. The sequence number you have is the first byte in the current stream that's being sent in this particular payload. So what is the number in the stream? So in this case 127 for this guy, and your port, you're told that source port number and destination port numbers are 302. So source 302 and destination is 80, was it? 80 would make sense, yeah. So it's a HTTP. So you're using your browser here or something to access some web files. You've got a second one coming then straight after that. And your question A is, in the second segment, what are the sequence number, port number, and destination number? So we'll so the second segment here, well, the sequence number will be different. So the sequence number will be the first number of the first byte in the stream. So you're told that the payload here was what was the payload? It was 80 bytes, was it? No, it was first and second contain 80 and 40. Yeah. So the payload is 80 bytes. So you know therefore that the sequence number here for this guy must be 127 plus 80. So 207. And everything else stays the same. So source and destination number are the same. Okay, so same. Why would they be different? It's coming from the same source to the same destination, so nothing's going to change. So that's part A. That was pretty easy, right? So part B, let's go back to the board or to the paper. So if the first segment arrives before the second segment in the acknowledgement, so the first segment arrives before the second, yeah. In the acknowledgement of the first segment, what is the acknowledgement number, source port number, source and destination port number? Alright, so that's pretty straightforward. So here's our acknowledgement, we'll say, coming back here from our first guy. What is the acknowledgement number? So the acknowledgement number is always the the next byte we expect in the stream, which is therefore 207, right? So so when we get an acknowledgement coming back here like this, it's always the next byte. So we know the next byte that we expect is 207. Indeed, it is 207 that arrives here. 207. And our source port number is the opposite, right? It's coming from port number 80, and the destination is the opposite of what we had up here. So they just flip. End of story. So that's part B done. Pretty straightforward. So I'll just do it in color code here. Alright guys, I can see you talking about the uploads. I really need to clean them up. There's a bit of duplication there because I edited them, got rid of the kind of the blank spaces where I'm not saying anything and things like that. So I will edit them and put everything up. I don't know exactly how. I'm a bit of a novice with YouTube, but it seems like any idiot can do it, so I should be able to figure it out. Where was I? So part B. So I've just done part B there. Let's have a look at C. So if the second segment arrives before the first segment, in the acknowledgement of the first arriving segment, what is the acknowledgement number? Okay, so the question there is, you know, let me go. Sorry, I'm trying to flip between my windows. Okay. So this was part A here, and this was part B. Pretty easy. And now part C is the question. The question is for part C is what would have happened if this guy was actually, what would the situation be if this first segment had actually arrived after, if it would have been delayed for some reason and arrived after over here? What would the acknowledgement be coming back here? So so I'll just use a different color here, maybe green or something. So we'll imagine therefore this actually arrives down here. So what would the acknowledgement be coming back? So in this case, it's going to, remember what TCP always does, it's always a cumulative acknowledgement. So you're always saying that the next byte I expect is whatever. So you know that the second packet here had sequence number 207 and it had payload 40. So therefore the next byte that would be expected at this point in time here, so what would have come back here, regardless of whether the first segment arrived before or after, would be the next, no, actually that's not true. So we'll imagine this this is I need to do it separately. It's just too confusing if I try and do it all in one timeline. Forget about that. Forget about the green line here. I'll just do it separately on a different graph. Tried to squash it all in. Pay the price. Right, so let's do it over here. So the first one gets delayed and the second one arrives like this. So because this was sequence number 127 and it had payload of 80 inside it. This one was sequence number of 207 and it had payload of 40. So so when it arrives over here, TCP will still say, look, I'm still expecting 127. So it's going to ACK number 127 back here. So it's saying, look, the next one I expect from you is still 127. I haven't received byte 127 yet. So I'm still expecting byte 127. So when this one arrives over here, it'll now realize it has 127, but it also has 207 and the payload of 40. So the actual acknowledgement that comes back this time will be 207 plus 40, so 247 will come back the second time. Hopefully you understand that one. Let me just see if there's any questions coming in. No questions coming in. Okay, I'll just keep going here. So part D. Okay. Now suppose that there are 5 more segments immediately sent after the first are sent, after the first 2, I guess, are sent, all with size 100 bytes. If the TCP window size is 5 segments, and if the first segment is lost, and all other segments and acknowledgements are sent successfully, okay, assume the timeout value is equal to twice the RTT, ignore any changes in the window size due to congestion control, draw a timing diagram to describe how all segments are out B. Okay, that's a nice question. So I'm just going to take a moment to rub out a little bit on the board here. So just have a little think about how we're going to do that one. Okay. Okay, so let's draw those first 2 segments again. So here's our timeline. So our first 2 segments come down here like this. You know, I'll give myself a bit more room because it'll help me to write all the details in here. So we'll say B is over here. So our first 2 segments come like this. This was sequence number 127 and payload 80. This was sequence number 207, payload 40. And you're told that there's now another 5 segments that are going to immediately follow, but you're also told that your window size is 5. So you're not going to be able to send all of these immediately, right? You're only going to be able to send 5 packets in the window. So the next 3 packets will follow here. So 1, 2, and 3. So we're going to have to wait to get back an acknowledgement from one of these guys, or at least the first guy here, before we can send another, so before the window can move across by 1. So if you're a bit confused by that, the window over here, in total there's 7 packets to send. So we'll just imagine we have packet 0, 1, 2, 3, 4, 5, and 6. But the window at the start is just stuck here. So we need to get an acknowledgement for 0 before we can move over by 1. We need to get an acknowledgement for 1 before we can move over. The window covers 5 and 6 and we can send them. So anyway, so this one here will have, we're told that they all have size of 100 bytes. So we just add on 40 to this to get the sequence number here for this guy. So this is going to be sequence number 247, and the payload is 100. So you add on 100. So sequence 347, payload of 100, and then 447, and the payload is 100. So let's have a look at the acknowledgements that come back. Okay, so here's our first acknowledgement here. So we know that this is ACK so it's the next byte we expect. So it's received everything up to 206. So it's expecting, next byte it expects is 207. So ACK number 207. This one will be ACK. You can just copy the numbers down here. So ACK number 247, 347, 447. What did I do wrong? 1, 2, 207, 247, 347. Yes, so the next one I expect now will be 547. Okay. What was the rest of the question? Now suppose there are 5 more segments. TCP is 5. First segment was lost. So you're told if the first segment was lost, that's what would have happened if everything was going well. Actually, just to finish off the story here, as soon as this was received here, my window would have moved across to so 0, 1, 2, 3, 4, 5, 6, and the same down here, 0, 1, 2, 3, 4, 5, 6. So my window would have moved across by 1, allowing 5 inside. So I would have immediately sent packet 5 with sequence number 547. And similarly here, this guy would have come across with sequence number 647. So these all have payload of 100. That's why I'm adding on 100 each time. And this would have happened because my window moved across to here. Okay, so that's what would have happened if everything had been going perfectly well. But of course, you're told that it was not. So the first thing you're told is if the first segment is lost and all other segments and ACKs are sent successfully, assume the timeout value is equal to 2 times RTT. Ignore any changes in window size. Draw timing time. Okay, so okay, so it's kind of hard to draw without a big long page here, like an A4 page, to do the double round trip time. So this is what would have happened. No problems. We'll just put in no problems here. No probs here. So what would have happened in the actual question? I'm going to do it a little bit faster here. The timeline would be a bit faster over here. So we'll go. So this would be 2 round trip times. Let me just do a quick 2 round trip times. That's 1 round trip time. 2 round trip time. I kind of ran out of room down here. I couldn't do my second round trip time. So we'll say that's 2 round trip times. So this won't happen, of course, for my first packet at least, because it's lost. My second packet would be the same. I'll just do different colors so it's clearer. My third. Fourth. And fifth, let's say. Okay, so you kind of need a long page for this one. So the first one is going to be lost. First one is lost. So we just get rid of all of this. This can't be sent again. In fact, the first one being lost is a bit of a problem here because it's going to hold up absolutely everything, right? So I need to work fast. 2 minutes. You know what? I've just made a bit of a mess of this. Sorry. It's easier to explain if I just do it one by one. I'll fly through this. As I can see the time. Okay, so the first packet is sent and it's lost. Second packet is sent and there's an acknowledgement that comes back. So this was number 127. This is number 207. So the acknowledgement that comes back here is going to be ACK 127, because 127 still has not been received. And if I look at my window over here, my window is going to be stuck. So my window is, so I've got packets 1, 2, 3, 4, 5, 6, 7 to send. My window, sorry, did I do 0? Do I call them 0? Yeah, sorry. So my window is here, and it's going to be stuck because I'm never going to get back an acknowledgement. So the base of the window is keeping it here. It can't move across. So I get back ACK 127. Similarly for the next bunch, so this is going to keep ACKing 127, even though it's buffering each of these guys. These 5 guys have arrived, and I'm still getting an ACK 127 coming back. Now, an ACK 127. So this is where I get my triple duplicate. Okay, so it's the 4th one that I get my triple duplicate here. Okay, so this ACK is going to come back. It's going to be all these ACKs coming back here. The 4th ACK is my triple duplicate. So this would actually trigger a retransmission at this point of packet 0 with TCP. So this will trigger 127 to be resent. And once it's received, everything else will be everything else, the gap will be filled in. So I'll be up to here to 447. So I'll send back an acknowledgement that comes back now saying the next byte I expect is 547. I know I'm going really fast here. The next byte I expect here is 547. And so the window will suddenly jump across. At this point the window will go, so the window is 0, 1, 2, 3, 4, 5, 6. Suddenly the window will just jump across all the way to here. And I'll be able to send packet 5 and packet 6 immediately. Okay, and the ACK so that would be packet 5. So I don't really have to worry about my timeout in this particular case. So you were told the timeout is 2 times the round trip time, which would bring you down to here, but it doesn't matter. The triple duplicate happened way earlier than 2 times the round trip time, so that triggers the retransmission and gets everything back online very quickly. And since I don't have any time, I'll just say it. So part E was to do this with GBN. I'm getting loads of questions coming in here. Why does the 3rd ACK 127 not trigger? Right, so it's a triple duplicate. So a duplicate would be a second copy, right? So a triple duplicate is a 3rd second copy, if you like. So the first one is just the original, and then the 3rd one is your triple duplicate. This is a duplicate, this is just a double duplicate, and this would be a triple duplicate. So that's why we use the term. So it's not the 3rd ACK, it's not the 3rd ACK that's the triple duplicate, it's the 4th. So duplicate kind of means there's 1 extra. A triple duplicate means there's 3 extra on top of the original. Okay, so any other questions coming in here before I go? So the last part here was, let me just jump over. Yeah, so was to repeat this for GBN, which protocol delivers all 7 seconds faster. So with GBN, what would happen would be you wouldn't discover the triple duplicate wouldn't trigger the retransmission. You'd have to wait for the timeout to happen, and none of these, all of these packets here would have been discarded with GBN. They wouldn't have been buffered. So when we eventually got packet 0 arriving here, we already had buffered 1, 2, 3, 4. So it filled the gap, and we were able to deliver all 5 up at the same time, and therefore move the window across. So with GBN, the buffering doesn't happen, so we just throw it away, throw it away, throw it away, throw it away. So once the timeout happens after 2 round trip times, we're going to trigger all 5 being retransmitted again, and we have to wait for the first one to be acknowledged before we can send packets 5 and 6. So it takes a lot longer. Yeah, and I don't have time to go through that, but yeah, that's what happens. Okay. I will leave you there. I'll chat to you soon. I have recorded loads of videos. I just have to put them up, so I'll do that. I'll try and do that now. Actually, I have about a half an hour. I'm going to try and do that now. It actually takes a long time to it takes about an hour to edit these things and put them up online. But anyway, my problem. I'll do that now. So chat to you soon. And good luck in your lab exam next week, guys. And thanks for sticking around. I don't seem to get too many, but there you go.